Hey there, geometry students, and welcome to Chapter 8 in our Big Ideas textbook, which is all about similarity. You can see a little overview here of the 4 sections in Chapter 8. We're going to be talking about similar polygons today, and then eventually we'll be going to proving triangle similarity by the AA, that's angle-angle, theorem. There'll be SSS, side, side, side. We saw that kind of before, and an SAS. We saw these kind of before. And then the last one would be proportionality theorems. So on to 8.1. So we're talking about similar polygons in 8.1. How are similar polygons related? So we're going to be using similarity statements. We're going to find corresponding lengths in similar polygons. We're going to find perimeters in areas of similar polygons, and we're deciding whether polygons are similar here in this lesson. All right, but first let's do a little cartoon. There's another Far Side. What did I say, Boris? These new uniforms are a crock. I love this one with the bull's eyes on their uniforms. Somebody didn't order those correctly. All right, so into the vocabulary, which is on page 223. There's 3 vocabularies. Let's just start with these 2, and these are actually review vocabularies. So we're talking about similarity transformations a little bit and similar figures here in this chapter. So similar transformations, a dilation is a transformation that preserves shape but not size. We saw that back in chapter 4 about dilations. Dilation is a non-rigid motion. So a similarity transformation, here's what kind of you can write, is a dilation or a composition of rigid motions and dilations. So that's what you can kind of put down for that right there. Right here, dilation or composition of motions and dilations, rigid motions and dilations. 2 geometric figures are similar figures if and only if there is a similarity transformation that maps one of those figures onto the other. So similar figures, that is when a similarity there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape but not necessarily the same size. So that's what we're going to see here in this one. We're going to see similar shapes but not necessarily similar sizes. Congruence transformations preserve length and angle measure when the scale factor of the dilation is not equal to 1 or negative 1. And we're going to be talking about scale factors today. That's another thing we'll be looking at. Okay, so you can stop this if you need to continue to copy those down. But on to the next vocabulary, which is corresponding parts. And we're looking at really on this core concept. And you don't really need to write anything down for this one on the vocabulary because it's kind of right here. Corresponding parts of similar polygons. This is definitely something you want to see. So we have to see there's 2 parts of this. Corresponding angles and then the side lengths are not necessarily congruent. The angles are congruent, but the side lengths are actually going to be proportional. So you want to do some highlighting in this here. So we have these 2 things, a similarity transformation. Here's this figure to this figure. You can see same shape but different sizes. It's a dilation. This one's smaller, this one's gotten a bit enlarged. So it's a dilation. But what's true about this is that the angle measures are still going to be congruent. So it says a similarity transformation preserves angle measure. So you want to highlight that part right there. Similarity transformation preserves angle measure in your notes. Corresponding angles are congruent then. That's how you know that. The corresponding angles there will be congruent. So you can see these are your corresponding angles, A and D are corresponding, and so on. But a similarity transformation also enlarges or reduces side lengths by a scale factor of K so that the corresponding side lengths are proportional. They are proportional. They make fractions that are equal to each other. They are proportional. And they're all going to be simplified down to K, which is going to be considered a scale factor, the scale factor of K. And so we'll be looking at what scale factors are again. All right, so here's one where it just says find the scale factors, like we said. So in this diagram, these are similar. So they are similar. It tells us that. Find the scale factor. Now you can just watch this one as we look at it. So if we want to find the scale factor, we're going to have to look at the side lengths and kind of take a corresponding side length. It doesn't matter which one. Let's see which one they're going to do. x, y, and rs. So x, y, the 12 down here, rs, the 20, they're going to put 12 over 20 and just reduce it. That will give us our scale factor. In fact, you can see they're all going to reduce to that 3/5, and so that means that 3/5 will be your scale factor. They all will have the same reduced fraction. These are all proportional. 12 over 20, 18 over 30, 15 over 25 are all proportional because we can reduce them all to the same fraction. List all pairs of corresponding angles. So we want to see, okay, which ones are corresponding, and it should be pretty clear to us which ones are going to be corresponding, which one looks similar. R and X, those ones. S and Y and T and Z are all the ones that are corresponding. Write the ratios of the corresponding side lengths in a statement of proportionality. So you're just going to put these all here, and you're just going to say they're all equal to each other. So the xy over rs, yz over st, and so on. Just you write in a proportionality statement saying all of these fractions here with the letters of the side lengths are going to be equal to each other. Okay, so on the page 224, if you turn over to that page, the very top, we have this core concept, corresponding lengths in similar polygons. If two polygons are similar, then the ratios of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. Okay, so that's something that we just need to keep remembering about this is, if we know the scale factor, we could see that if we just take any two, so that's what we kind of saw. We, on that last one, we could have just taken two of those. If we know they're similar, if we already know these two, and that's what it told us, and that's what it said back here on this one, it tells us these are similar right here. So we know we can just take, it doesn't matter, we can just do these two, and that would give us the scale factor right there of the 3/5. We don't have to do all three. We could just do the first one because of this little core concept right here. If two polygons are similar, that's what it told us, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of those similar polygons. So that's what I'm saying here is we only need just to look at one side length, not all three. Yeah, on this problem, we're trying to find the value of x. Again, it's telling us that these are similar. So if we want to figure out the volume of x, we just need to make a kind of a proportion out of this. And again, you're not writing this one down, just watch this one. This is, again, a book example. So we're going to be making just a proportion. So you can just choose two sides. One of them has to be EF here, where the x is. So they're going to be choosing that one EF down here. And NP, which is the corresponding side, would be on top of that. And you can make your proportion any which way, really. I could have put EF over NP this way. There's more than one way to write a proportion. So then we just need to figure out what's another side length, another corresponding side length. They're using MN. So that's going to be this one right here, the 18 and the 15, the DE. So those are the other two sides they chose. They did not choose these two. They could have if they wanted to. And then you just plug everything in, cross multiply to do this. So 18 times x will be 18x, 15 times 30 gives us 450, and then just divide by that to get your x number. So very similar to solve a proportion. Okay, on to the extra practice on page 225 right at the top. We're looking to find the value of x. It tells us that the polygons are similar. So we're just going to make a proportion out of this, starting with where x is. So x is here. The corresponding side to x is going to be where 7 is. So I just usually put x over 7. Make it real easy for myself. So it's just x over 7 is one fraction. Then the other one that we're going to see is this other corresponding side, the 2 and the 3. So in order to make sure that we do get this right, I cannot put 3 over 2 because that wouldn't be correct. So if I'm going to be putting x on the top, I got to put 2 on the top because they are going to be from the same shape, same figure here. So I'm going to have to put it as 2 over 3. So now we got this is proportional here because the x and the 2 are from the same one and the 7 and the 3 are from the same one. So make sure that's going to be true. And then just cross multiply, so x times 3 is 3x, 2 times 7 is 14, so 3x is equal to 14, and divide by 3. So we're going to see x is equal to a 14/3, or if we want to change that to a mixed number, it's 4 2/3. The decimal form of that would be like 4.6 repeating, so I might just leave it as a fraction, I think. Over here on this one, number 2, so x is over here, so the corresponding side on this one, we got to figure that out. So it's between 1 and 3. So over here, here's 1, here's 3, so it's got to be 25. X is corresponding to 25, so we'll put X over 25. And then we just choose another one. It doesn't matter which one you choose. You have 2 to choose from. So I chose the 8 and the 20. So 8 is between 1 and 2, and so 20 is also between the 1 and the 2 marks down here for the angles. Make sure that those are corresponding to each other. So it's 8 and X are on the top because they're from the same shape. These are also from the same shape. Just make sure that's always going to be true. If you switch that, then that would not be proportional. So putting 20 over 8 here would not work. So now you're going to cross multiply. 20 times X is 20X. 8 times 25 is 200. And just divide by 20. So that's going to give us X equals 10. And that's it. Okay, here's another book example. It shows us this diagram here. It says the triangle TPR is similar to triangle XPZ. That's the black triangles here. So this triangle over here is similar to this triangle over here. And so it says find the length of the altitude PS. So that's this altitude here. Now it does tell us the altitude of this triangle from P to Y is 20. So the first thing we're going to want to do is figure out the scale factor of these two similar triangles. And so to do that, we're going to be adding up. So this side here, 6 plus 6 would give us 12 for the top of TR, and then 8 and 8 would make 16 for the bottom. And we could just simplify 12/16 to 3/4. So there's the scale factor of these two triangles. Now, we need to realize that because the ratio of the lengths of the altitudes in similar triangles is equal to the scale factor, you can now write this proportion. So if we, and you can do this anytime, the altitudes is always going to be going from a vertex down to an opposite side at a 90-degree angle. That's why you can see these right angles here. That makes it an altitude. It's not just some line going through. It's perpendicular to this XZ side. This one's perpendicular to TR. And so we can write a proportion now with the altitudes and say that PS over PY, that's the altitudes here, PS here over PY is equal to 3/4. So we're looking at the smaller triangle on top and the bigger triangle on the bottom. That's what we have up here. So the smaller altitude on top, the bigger altitude on the bottom. And now we know what this bigger altitude is. It's 20, so we can now replace PY with 20 and then just cross multiply. That's going to give us 60 here. So it'll end up being 15. So we see we're going to divide by 4. So 60 basically divided by 4 is 15. That would tell us what PS is. Okay, so now we're going to get into finding the perimeters and the areas of similar polygons. First, we're going to look at the perimeters. This is on page 224, right there in the middle of the page. We're going to actually write in the notes underneath that theorem on this next screen. So the theorem says that if two polygons are similar, then the ratios of their perimeters is equal to the ratios of their corresponding side lengths. So basically what that means is that if we have these two are similar, if we're told they're similar, so these two shapes here, they are the same shape but they're different sizes, like a dilation. Okay, so they are similar figures. They are similar polygons. So what we could do then is we could figure out what the perimeter of one is. So we can add up all the sides of this one and add up all the sides of this one. So they're putting the bigger one actually on top here, as you can see with the red. So adding all the sides of the bigger one on top, adding all the sides of the smaller one on the bottom, and then they're going to say it's going to be equal. So if you take the perimeter of that, whatever that is equal to just taking the side lengths, whatever the side lengths are. So really it's going to be similar to like the scale factor. And that's what it says, that it's equal to like the scale factor. Alright, so let's take a look at what we're going to write underneath this theorem. We'll do one problem here. Okay, so this is to go in the notes section under theorem 8.1 on page 224, just that little spot right underneath there. What you could do is you can just a little quick sketch of these and then just say find the perimeter of gazebo A, or find the perimeter of A. If you just want to say A and B, you can just label them A and B. and then do a little quick sketch if you can, labeling them with the letters around and also the numbers for the side lengths. And if you need to pause the video to do that, then you can, and then continue to start it from where I'm going to talk now about doing this. First thing we need to figure out is the scale factor of our similar figures here. So the scale factor I'm going to do start with A and B, A on top and B on the bottom. So what we do know is we know AB side here on this gazebo A. We don't know any other side. In fact, it tells us X here. That's actually kind of throwing us off there. We don't have to find X. It doesn't say to find X anywhere in here. It just says to find the perimeter. So that really doesn't, it's not necessary for us to figure this out, to figure out what the perimeter is. But as long as we do have this right here, one side length on this figure, we're good. So now I can take this AB and put it over this FG for scale factor. That's going to be 10 on the top and 15 on the bottom. And so we just simplify that down to 2/3. So our scale factor would actually be 2/3. And alright, well, this bar got in the way here. Sorry about that. Just a scale factor. At that point, we now need to figure out what the perimeter is of gazebo B, and we can do that because we have all the side lengths for gazebo B. So perimeter of B is going to be adding all these sides up. So 15 and 15 make 30, 18 and 12, that also makes 30. So that makes 60 plus 9, so our perimeter is 69 meters for gazebo B. So now what we're going to do is take the scale factor, our 2/3, and make a proportion out of this. So the scale factor is 2/3, and the ratio of the perimeters is equal to the scale factor. It's equal to the ratio of any two side lengths here, corresponding side lengths. So it's equal to the scale factor. So I can take the scale factor, the smaller one's on top, so A is on top and B is on the bottom. So I'm looking for A. I know B is 69. So it's going to be perimeter of A on top, looking for A. The perimeter of B is 69. And now it's a proportion I can go ahead and solve. So 3A, and then 2 times 69 is 138. So now I just divide by 3, and 138 divided by 3 equals 46. And there's our answer for A. The perimeter of A then is 46 meters. That's all they asked us to find. Okay, so let's take a short little break here and do an episode. This is new this time. An episode of Captain Literally to the rescue. Captain Literally. I don't know if you've seen this before, but hope you enjoy.
Man, this movie is intense. I am literally glued to my seat.
I know.
What are you doing?
Teaching you to be more cautious with your language, sir. Whenever someone misuses the word literally, it is my job to literalize their reality and restore balance to the universe. Now, how does it feel to be literally glued to your seat?
Weird.
Is this in any way comparable to the feeling you get when the excitement of a film makes you strongly desire to keep watching?
No.
Excellent. Balance restored!
Thanks, Captain Literally.
This book is so good, it'll literally fly off the shelves.
Balance restored!
We're married. I am literally on top of the world.
Where did you send him?
I'm not sure, actually. I've never understood that phrase. Balance? Yeah, balance probably restored. I need some cake.
I hope you enjoyed that first episode of Captain Literally, who restores balance. Alright, so moving on, we're going to go on to now the areas of similar polygons. So we did the perimeters, now we're looking at the areas. So it's almost the same kind of thing, except on this one, if these two are going to be similar again to each other, we're looking for the area on the inside of these shapes. So we would want to, see the area of the one. So you could see the blue ones on the bottom here. They put the red one on top. Now it doesn't matter which one you put on top and the bottom as long as you're consistent in doing things. So they found the area of the blue one, put it on the bottom. They found the area of the red one, put it on top. And what that's going to be is if two polygons are similar, then the ratio of their areas is equal to the squares, and circle that or highlight that, the squares of the ratios of the corresponding side lengths. So basically we could find the scale factor again, just like we did with the perimeter, except this time it's not equal to the scale factor, it's equal to the scale factor squared, or a ratio of the sides squared. I usually like the scale factor because it makes the numbers smallest or in simplest form for me. So I usually just make it always the scale factor and do the scale factor squared. Okay, so we're going to also do the same thing and put some one example right there at the bottom of 224. Okay, so this is going to be at the bottom of page 224, just underneath that theorem 8.2 that we were just looking at, about finding the areas of similar polygons. So we have two similar polygons here. Looks like they're rectangles, but we're not told that, but we don't need to know that. Just that they're quadrilaterals. We want to find the area of L, M, and P. That's this bigger one. It tells us what the area right here of GHJK is. That's the smaller one. So we know the smaller one's area is 84 meters squared. And we need to use some side lengths here. Here's corresponding side lengths with 7 and 21. So go ahead and right there, just copy this down, copy the figures down, the little rectangles. Copy down that the area of this one is 84 meters squared. We got the 7 here, the 21 over here. So that's what you want to copy down as we start to work through this. Okay, so the first thing that we're going to need to do here is identify where we're going to put this in a fraction. So we're going to make some kind of a ratio out of this, the ratio of the areas to the ratio of the side lengths or the corresponding sides. So the ratio of the areas and this corresponding sides, I'm going to put the smaller one on top and the bigger one on bottom. So it could be the other way around, but I just chose to put the smaller one on top and the bigger one on bottom. For this one, we're going to consistently keep the smaller one stuff on top. Hang on a second. Okay, I want to get that bar out of the way. Okay, so we got the smaller one on top and the bigger one on the bottom. So we're going to put as far as the areas, this is going to be now the area. So one ratio is going to be your areas. So a ratio of the areas is going to be, the smaller one is 84, and I'm using X to represent the area for the bigger one, the L, M, and P that we're trying to find. And then I'm going to set it equal to the corresponding sides here. So I'm going to put the smaller one, the 7, on top and the 21 on bottom, and it's going to have to be squared because the ratio of the areas to the ratio of the corresponding sides, it's going to be the square of the corresponding sides or the square of the scale factor. So we could write it like this with 7 over 21, but I would prefer to reduce 7 and 21 down to 1/3. That way it's just a little easier to work with. 1/3 really is the scale factor. That really is your scale factor as I reduce that down. So it's always going to be squaring the scale factor. Your ratio of the areas is going to equal the scale factor squared. And so that's what we got to remember on this one. We got to square the scale factor or square the 7 over 21. So as first of all, we got to square the 1/3. So 1 squared and 3 squared, that will give us a 1/9. So now we have a proportion that we can solve, and so we got x times 1 is 1x, and just going to multiply 84 times 9, and it's going to give us 84 times 9, it's not 84.9, it's 84 times 9 is 756 meters squared. So that is our answer for this one. That is the area of the LMNP. Okay, here's one more book example. It just says decide whether A, B, C, D, E, it's this blue one and this red one here are similar. Explain your reasoning. So as we're looking through the corresponding sides on all of these, so right here, this is where an angle is. These angles are definitely showing that they're congruent. So there are 12s here, there are 8s here. So we could make some kind of a scale factor and see if they all will come out to be the same scale factor. And you'll notice what it says here, that all the corresponding sides have a scale factor of 2/3. So 8 over 12 is simplified to 2/3. 6 over 9 reduces to 2/3. 4 over 6 even reduces to 2/3. So that's all going to be 2/3. But that's not only what we can do here, so it just doesn't look right. As you're looking at this, it just doesn't seem like these are similar figures. Are these really similar? So we want to continue on this one, even though all the scale factor is the same. It says here, however, this does not necessarily mean that the pentagons are similar. A dilation with center A and scale factor of 2/3 can move this on to that one here. And so then we want a reflection after that. So basically what we're going to do here is put a line straight through this. We're going to shrink the blue one down to this green one. And then we're going to just flip that over the reflection line here and see, does it really match up with the red one? And you can tell it doesn't. So that just by looking at that now we know these aren't similar. So we can't just go off of the corresponding sides all having the same scale factor. Okay, we're almost done. Back to the extra practice. We just have 3 to 8 now to complete. It tells us that we have 2 polygons here. They're both 5-sided polygons, that they are similar. And so we're going to be answering these problems here from using this diagram over on the side here. So number 3 says find the scale factor from the ABCDE, that would be the smaller one, to the larger one. So the scale factor from this one to that one, so that means the top number is going to be from the smaller one, the bottom number is going to be from the larger one. So it's going to be the scale factor here. I'll just use AB and KL as a scale factor. I could have used DE and NP, I could have used those. But AB is the smaller one, it's on top, KL, the bigger one on bottom. So that means that 2 is on top and 3 is on bottom. So our scale factor from the smaller one to the bottom to the bigger one is 2/3. Then it says find the scale factor from the bigger one to the smaller one. So all you have to do is just flip this upside down, take the inverse of this. So it's just going to now be KL over the AB. So now it's just 3 over 2, or 3 on top and 2 on the bottom. So the scale factor from the bigger one to the smaller one would be 3 over 2. Number 5, we're looking for the values of x, y, and z. So x is over here. There's 2 places where there's x. X is both of these. So in this one we want to look at setting up some proportions to find x. So we already know the scale factor, which is 2/3. If we go from the smaller one to the bigger one, and I'm going to use that. I'm going to use the 2/3 here for finding x. So I'm going from the smaller to the bigger. So now if I see x is also corresponding to 1. So 1 is the smaller, x would be the bigger one. So 1's got to be over x. So 2/3 has got to equal 1 over x. It can't be the other way around. And so now we're just going to cross multiply. So 2 times x will be 2x, and 3 times 1. So we get 2x equals 3, and then just divide by 2, and x is going to equal 3 over 2 or 1.5. So I'll plug those in here. So these are both 1.5s here. So now I know these side lengths in the bigger one. To find the value of y next, so y is this longer side here, which corresponds to AE, the 3 square root of 2 here. So we're going to still use the scale factor again. I'll use the 2/3 from smaller to the bigger. If I wanted to go from the bigger to the smaller, I would do the 3 over 2. But I'm just choosing to go from smaller to bigger. Doesn't matter which one you choose, which direction you choose. So 2/3, that's the scale factor. And we're going to go from the smaller one, that's the 3 square root of 2 on the top, y will be on the bottom. So it's going to equal 3 square root of 2 over y. So there's another proportion that we now can cross multiply. So 2 times y is 2y. 3 times 3 square root of 2, we can multiply the 3 since they're both on the outside. So 3 times 3 will be 9 in front of the square root of 2. So it'll be 2y equals 9 square root of 2. Divide both sides by 2, and we'll have y equals 9 square root of 2 over 2. And I'm going to write it over here, and what we could do is we could also see the 9 over 2 as a fraction in front of the square root of 2. So I'm going to write it over here like this. 9 halves in front of the square root of 2. So we could put it like that. Or if we want to see that as a decimal, we could see it as 4.5 square root of 2. Number 6 is find the perimeter of each polygon. So finding the perimeter of I didn't find z yet. I need to find z still. Z, I forgot about that one because it's an angle. So it's angle A right here, which should correspond with angle K, and all the angles in similar figures are going to be preserved. So if this is 45, then Z is also has to be the same of 45. So Z is 45 degrees. Okay, so now on to 6, finding the perimeter of each polygon. We'll start with the smaller one, A, B, C, D, E. So I'm just going to count up what I have here. So I have 2 plus 1 is 3, plus 1 more is 4, plus 2 more is 6, and then 6 plus this 3 square root of 2. There's no way I can put that together. I just have to write it that way. So I have 6 for kind of a whole number, and then plus the 3 square root of 2 after that. That's how I'm going to write out this perimeter, 6 plus 3 square root of 2. If I needed to figure out the decimal form of this, I could. I could figure out the decimal form of square root of 2, multiply it by 3, then add 6. For the bigger one, I'm going to do kind of the same thing now that I know what these other side lengths are. So I have the 3 plus a 3, that gives me 6. 1.5 and 1.5, that also makes 3. So now I have a 6 plus 3 more is 9. So I'm going to see 9 in front of this radical here, 9 over 2 with a square root of 2. So 9 is the whole number plus this radical here, 9 over 2 square root of 2. Number 7 says find the ratio of the perimeters of the smaller one to the larger one. So we got to go back up to the scale factors. Smaller to larger is the 2/3. So we're going to use 2/3. So I'm going to use the same ones, AB and KL. So AB and KL. Now remember that this is the perimeters. The ratio of the perimeters is the same or equal to the ratio of corresponding sides, which is the same as the scale factor. So that would be the 2/3. So this is the ratio of the perimeters is 2/3. So that will actually be the answer. Even though that is the scale factor, that is also the ratio of the perimeters. So the ratio of the perimeters is equal to the ratio of corresponding sides, as we learned earlier, which is the same as the scale factor. Number 8, find the ratio of the areas from the smaller one to the larger one. The only difference here now will be from smaller to larger, so same thing. We're going to use AB over KL. The only difference now is it has to be squared. So the ratio of the areas has to be basically the ratio of corresponding sides squared. And so I'm going to square it now. So AB over KL is going to get squared. So I'm going to say 2/3 is going to get squared. So 2 squared on top and 3 squared on the bottom. So that's going to give me 4 on the top, and on the bottom 3 squared will be 9. So the ratio of the areas is actually 4/9. So realize that the ratio of the perimeters is the same as the scale factor. The ratio of the areas is basically the scale factor squared. That will give you the ratio of the areas. Alright, so that concludes 8.1, and stay tuned for the next one on 8.2. I'll see you in class.